The Wittig reaction, video by Dalton. The Wittig reaction begins with the formation of the Wittig reagent, which is formed with a primary or secondary alkyl halide and a triphenylphosphine under basic conditions. First, triphenylphosphine performs an SN2 with the alkyl halide, kicking out the halide. Next, the carbon is deprotonated, forming a carbanion. This structure is a phosphorus ylide, also known as a phosphorane. This ylide has a resonance with a double bond to phosphorus, but it will react in the ylide form. Put simply, the Wittig reaction is the Wittig reagent reacting with a ketone or aldehyde to form an olefin, also known as an alkene. What's tricky about the Wittig reaction is specific substituents of the phosphorus ylide, the carbonyl, and the solvents used affect the transition state, which determines the conformation of the product, E or Z. In this video, I will focus on a non-stabilized Wittig reagent and an aldehyde to simplify the transition state explanation. First, we must consider the size of each group on the Wittig reagent and the aldehyde. The aldehyde is simple, the hydrogen is small, and will be smaller than whatever the R group is. The ylide has one very big group, triphenylphosphine. When it's written out like this, it does not look too big, but let's briefly remember its actual structure. There are 3 phenyl groups bonded to a phosphorus. We can comfortably assume the R' group is smaller than this. Now, the ylide and aldehyde will line up, so to say, for the first nucleophilic attack. To reduce steric interactions, the triphenylphosphine will line up with the hydrogen. There will be some sterics between the R and R' groups, but we avoid the main steric interaction between the PPH3 and R group. Once in the least sterically hindered position, the carbanion of the ylide will act as a nucleophile and attack the carbonyl electrophile, pushing the electrons up onto the oxygen. It is important to draw this step and the following steps out in 3D, so the conformation of the product can be determined. The carbon-carbon bond just formed will then rotate, and the now negative oxygen will act as a nucleophile and attack the positively charged triphenylphosphine electrophile. Here, a 4-membered ring is briefly formed as part of the transition state. This conformation has considerable angle strain and quickly collapses. Both the carbon-phosphorus bond and the carbon-oxygen bond will break, forming 2 new pi bonds, the olefin product and a phosphate ion. This last step shows why a 3D model is so important in determining the Wittig Olefination product, as we are able to see the orientation of the R and R' groups. They are syn to each other, and therefore the major product we see is the Z conformer,